So numerical integration. So many times we are not able to carry out the exact analytical integration. So we require to do numerical integration. So for that, first we should understand certain terms. Before we go into integration, we will write differences. That's important because based on that formulas are developed. So finite differences so let y equal to f of x be a function with the following set of discrete values. So x value can be x0, x1, x2, so on up to xn. Y value is y0, y1, y2 up to yn. Okay. Now such that we have control over x. We are making intervals over x. That means each interval, the difference between x1 and x0 is h. The difference between x2 and x1 is h. So now we define what is called as the forward differences. Forward differences. Now we say delta y0 is y1 minus y0. Forward difference means we are taking the next point. Next, suppose I want to find the difference, change in the value of y at y equal to 0. We take the higher, the next point in the sequence and take the difference, that is forward difference. So similarly, delta y1 will be y2 minus y1. So on. Delta yn is yn plus 1 minus yn. So in general, so we write yr is yr plus 1 minus yr for r taking values from 1 to n. So this is called as, so this is a general term representing all of the above. So this is called as the first forward difference. This is called as the first forward difference. Now, and delta is called as the forward difference operator. It's called as the forward difference operator. operator. Now, second forward differences. Second forward differences is defined as delta square yr, which is the difference delta r plus 1 minus delta r. So this is the second forward difference. Now, third forward difference delta cube yr. Okay, so this will be delta square yr plus 1 minus delta square yr, so on. Next, we take the backward difference. This is forward differences. Next, we consider the backward difference. So, in backward difference, we denote by nabla. Nabla is the reverse operator. It is not delta, it is nabla. Nabla y1 will be y1 minus y0. You are going back. You are taking its difference from the previous step function value. So, nabla y2 will be y2 minus y1, so on. Nabla yn will be yn minus yn minus 1. Okay. So the first backward difference. So in general, this is delta, the nabla yr will be yr minus yr minus 1. This is the first backward difference. Now, we want to find the second backward difference. Nabla square yr. What will that be? Nabla yr minus nabla yr minus 1. So this is the second backward difference. And then the next third backward difference, nabla yr will be nabla cube yr will be nabla square yr minus nabla square yr minus 1. the third backward difference. So, and so on. So this goes like this. Next. Next we do central differences. Central differences, how they are defined. They're defined like this. We define with this small delta, delta y half is y1 minus yz. Okay, this is delta y half. Central difference. So these are 2 points at x1, y1, x0, y0, x1, y1. Now the central x0, y0, x1, y1. Now, at which point do we consider the difference? We consider at this point. We write this as y half, x half. This will be x naught. This is x1. So exactly take the middle point. Now how to, so here is my central difference. So is I define that the central difference is y1 minus y0. Similarly, delta y3 by 2 is y2 minus y1. Okay. Similarly, delta y5 by 2 is y3 minus y2. Okay. Similarly, delta y, let us see, this is y, yeah, yn minus yn minus 1 will be yn minus 1 by 2. Because add these two, n plus n minus 1 divided by 2. So that will, this will be this one. So this is the central difference. So in general, this is called as the first central difference. Now, delta square is the second central difference. So if I write this like this, delta square y1 will be, it will be delta y3 by 2 minus delta y1 by 2. So exactly a number which is in between is 1. So plus half minus half. Like that we have to see. Now this becomes, you can see this, y2 minus y1 minus y1 minus y0. So we get y2 plus y0 minus 2y1. So this is the general central difference formula. Okay. So next is what, with this we move forward to integration. Once we understand this, so first we will describe what is called as the Newton-Cotes formula. So numerical integration. Hmm. I'll do this. So in general, numerical integration may be stated as follows. This is a set of data points x0, y0, x1, y1, xn, yn of a function. Y is equal to f of x, where f of x is not explicitly known. Okay, we do not know the exact value of f of x. We only know data points. We don't know the full function. If we know the full function, we can solve, but numerical integration is done when we don't have a clear idea of this function, or you have an idea of the function, but you cannot integrate it by standard methods of integral. So it is required to compute the following definite integral. I is equal to integral a to b y dx. As in the case of numerical differentiation, we replace f of x by an interpolating polynomial and obtain on integration this is phi of x and obtain on integration an approximate value of the definite integral. Thus, different integration formulas can be obtained depending on the type of interpolation formula used. So, what exactly is a definite integral? So, if we see this, I want to integrate from points A to B. Now, I don't know the function, actual function. I don't know the curve exactly. But integration basically means area bounded by the curve and the x-axis, and between these two lines, x equal to a and x equal to b. That is integral. Now the problem is we don't know. We know only points here. We can call this as x0, x1, x2. So this is x1. This is x2. This is x3. So on. This is xn minus 1. And this is xn. B is xn. Let us say. So we start with this. Now, what is integration? Now I don't know this curve. I don't exactly know this curve. So I have to approximate this curve between these 2 points. Okay, this point and this point. I have to approximate. How do I approximate? So depending on my approximation, I will get a different formula. So we call this as the interpolation formula. Function being approximated between 2 points. If we approximate with a straight line here, we get a trapezium. Then we call it as the trapezoidal rule of approximation. Or if we do by a quadratic curve approximation, so then we get the Simpson's rule like that. So we have different levels of approximations. Now, let the interval AB be divided into n equal subintervals as I've shown here. Clearly, xn is x0 plus nh. Hence, the integral becomes integral x0 to xn y dx. Okay. Now, approximating y by Newton's forward difference formula. So why we had to do those differences is here. Now, what is this formula? What we write is, this is actually a Taylor series expansion, but numerically written. So y can be written as, I'm writing explaining this here. So Newton's interpolation formula. So suppose you have f of x naught plus p times h. P can be some value. So this is by Taylor's series approximation, f of x naught plus ph into f dash x naught by 1 factorial, and p square h square by 2 factorial into f double dash x naught, okay, plus p cube h cube by 3 factorial, f triple dash x naught, and so on. Now, how do we write these formulas? So we write like this. Now, this f dash of x naught, we write as, say, delta y naught by delta x naught. Change in y by change in x. Now, if we use the forward difference formula, now how we write this depends on the different formulas that we used, either forward difference or backward difference or central difference. Now I'm choosing forward difference, so y1 minus 0 by x1 minus x0. Now this is y1 minus y0 by h. x1 minus x0 is h. So I can simply write this as delta y0 by h. Okay. Now what will be f double dash x naught? F double dash x naught will be delta of f dash x naught by delta x naught. Second difference. This is delta f1 minus delta f naught by delta x1. So this basically we get is what we get is the second difference of y naught divided by h. Okay, so on. So when we substitute this, we can see here, we can substitute this. Now f dash x is y naught delta y naught upon h. Okay. Next, we will write p square h square upon 2 factorial into this one, f dash. So you get delta square y naught upon h. Delta square y naught, you will get further results. Okay. So this comes out to be like this. So I am explaining how we get this expression here. Okay, that's what I'm explaining here. So from here, what we get is Newton's forward difference formula can be written as so we can write this as f of x naught plus ph. We can write this as 1 plus delta, the operator, forward difference operator, whole raised to power p times y naught. We get this. We get y naught, f of x naught is y naught plus p times delta y naught. So, and then pc2, that is p into p minus 1 by 2 factorial into delta. So this turns out to be this. We can write this as this. formula, which is 1 plus P times delta plus P into P minus 1 by 2 factorial delta square plus P into P minus 1 into P minus 2 by 3 factorial delta cube, so on. This times y naught. This is the forward difference formula. So Newton's forward difference formula, we are approximating. Now depends on how many terms that we use. We will see one by one. This is the most general formula for interpolation. Next, Newton's backward difference formula. Next, Newton's backward difference formula. So we write f of x n plus ph is 1 minus delta raised to the power minus p times yn. This is the backward difference formula. So you get 1 plus p times nabla. This is not delta, this is nabla, plus p into p plus 1 by 2 factorial nabla square plus p into p plus 1 into p plus 2 by 3 factorial into nabla cube, so on. Operated on yn. So either you can use the forward difference or the backward difference. So here we use the forward difference. Approximating y by Newton's forward difference formula, we obtain this. Now, since x is equal to f of x is x naught plus ph, differentiating dx will be h times dp. H is constant, h times dp, and hence the above integral becomes h. So dx becomes h times dp. So h times dp times y naught into p delta y naught, p into p minus 1 by 2 delta square y naught, so on. As it is, it will remain. Which upon simplification, now this is, we have to integrate from x naught to xn. X naught to xn. Okay. So when we do that integration, upon integration, each term we have to do the integration separately, and then we calculate like this. Each term with respect to p, and then substitute the difference. So n into h times y into y naught plus n by 2 delta y naught plus n into 2n minus 3 by 12. And so how you get this is by integrating the terms. Okay. Now this, okay, this is, we are integrating from, oh, we are integrating, I'm sorry, this will not be xn, this will be 0 to n only. Why 0 to n? Because now the integral variable has changed to p. P varies from 0 to n. Okay. So upon this simplification, we get this. So this is known as the general formula. Okay. Or this is known as the general Newton Cotes formula. Now, we can obtain different integration formulas by putting n equal to 1, n equal to 2, n equal to 3. We derive here few of these formulas, but it should be remarked that trapezoidal rule and Simpson 1/3 rules are found to give sufficient accuracy for use in practical problems. So once we do this, what is Simpson's rule? We are using forward different first trapezoidal rule. In trapezoidal rule, we are setting n is equal to 1. So let us do this. Hmm. Trapezoidal rule. Now setting n equal to 1 in the general formula, all difference higher than the first one will become 0. So you see here, set n equal to 1. So only these terms you will get. When you put n equal to 1, you cannot take these negative values here. Just a second. All right. So, sorry. So when we set n equal to 1, what we are doing is we are approximating, we'll take now, let us say one step we take x naught to x1, x naught to x1. The approximation will be h times y naught plus half delta y naught. Now delta y naught is y1 minus y naught. Now when we simplify this, we get y naught plus y1 by 2. Similarly, for the next interval also, we are simplifying. From x1 to x2, we get h by 2 into y1 plus y2. Nth interval also you get by this h by 2 xn minus 1 plus yn minus 1 plus yn. So combining all these expressions, this is wrong. This should be 0 to n. So 0 to n will be x0 to x1, x1 to x2, x2 to x3, so on up to xn minus 1 to xn. So if we combine, we should be getting h by 2 times y naught plus y1 plus y1 plus y2, okay, plus y2 plus y3. So on. And you will get at the last yn minus 1 plus yn. Okay. So this becomes y naught plus 2 times y1 plus, because this becomes 2, this becomes 2, this becomes 2, this becomes 2, and here we should get plus yn here. Okay, I'll just change. So this is the trapezoidal rule. Now what it describes, what trapezoidal rule describes is this. Okay. So geometrical significance of this rule is that y equal to fx is replaced by n straight lines joining this point. Now area bounded by this curve, okay, is equal to these trapeziums. So I'll draw the curve properly. So between the 2 points, A and B. Okay. All right, we can draw it as a smooth curve to just show the approximation. Okay, this is y equal to f of x, which we don't know the curve. We don't know that this curve. Now what we approximate is Uh, okay. This is x1, this is x2, this is x3, this is xn minus 1. What we do is between x0 and x1, we are approximating these 2 points by a line like this, straight line. The next approximation for x2 is this line here. The next approximation x3, y3 again is with this line. So what we are doing, we are adding the trapeziums. What is the area of this trapezium? Area of a trapezium is half the sum of the parallel sides, that is parallel side here, this is x0, y0, this is x1, y1. So sum of the parallel sides y0 plus y1, half into sum of the parallel sides into the distance between them. Distance between them is h. Okay, that is what is happening here. H by 2 into y0 plus y1 here. You see, this is the area of the trapezium. Here again, the second term, the area of this trapezium will be half sum of the parallel sides times the distance between them. So adding up all the areas of trapeziums like this, we get an approximation that is called as the trapezoidal rule. Okay. We are adding up all the trapeziums. So the approximate equivalent sum of areas of n trapeziums obtained. This is the simple trapezoidal rule. Sometimes this trapezoidal rule is complicated by 4 points and 3 intervals. That means 3 trapeziums combined. Okay, those things will not follow. We simply get this trapezoidal rule. Okay. Next, the second thing, Simpson's rule and Simpson's 1/3 rule. There are 1/3 rule, 3/8 rule. We will see what is what. Now in Simpson's 1/3 rule, what we do is we take n equal to 2. So instead of having a simple straight line, we are taking n equal to 2. We take 3 points and replace the curve by n by 2 arcs of second degree polynomials or parabolas. So here we see n equal to 2 means we are approximating to first y naught plus delta y naught, that is the first difference, and the second difference. Okay. In the general Newton Cotes formula, what we do is this. So the second difference, so this gives us y naught plus y1 minus y naught plus 1 by 6 times the second forward difference is y2 plus y naught minus 2y1. So when we simplify this, we get h upon 3. We get h upon 3, y naught plus y2. In between, we get 4y1. So this is actually this is x0 to x2. This should be. This is x0 to x2. Just a second. It's not working. This is x0 to x2. N equal to 2. So we'll take two intervals. Then x2 to x4 will be h by 3, y2 plus y4 plus 4y3. Then x n minus 2 to xn, y dx is h by 3, y n minus 2 plus yn plus 4y n minus 1. So when we add all of these, we'll get h by 3 times y naught plus 4 times y1 plus y3 plus y5, so on. Then plus 2 times y2, y4, so on, plus yn. Now this, okay. This is actually x0 to xn. Okay. So this is what we get on summing up. So this is known as the Simpson's 1/3 rule. So this is known as Simpson's 1/3 rule, or simply Simpson's rule. Now what we are doing is, so here x0, x1, x2, we are simplified here. We are showing here, this is x0, y0. This is x1, y1. And this is x2, y2. Okay. Now these three, what we are doing, we are joining this by a quadratic curve. We are joining by a quadratic curve. So the approximation here is not a straight line. It is quadratic. So therefore, we get a result like this, that between integral x0 to x2 y dx, we have h upon 3 into y0 plus 4 y1 plus y2. This expression is a result of having a quadratic curve here. So one thing is, for Simpson rule, the divisions of the whole range should be divided into even number of subintervals of width h. That is the most critical thing. All right. Now, we can do higher level formulas. Simpson's 3/8 rule. It is not 3/6 rule. It is 3/8 rule. This is Simpson's 3/8 rule. Okay. Now we obtain by setting n equal to 3. When we substitute n equal to 3, we get this expression. We finally get so we get 3h/8 y0 plus 3y1 plus 3y2 plus y3, and from x cube to x power 6, we get 3h/8 y3, 3y4 plus 3y5 plus y6. So summing up all this is 3h/8 into this. So we get a formula like this, and this is called Simpson's 3/8 rule, but we don't generally use them so much. We just use the first two. Now truncation error formulas, this we will go through once. We'll just go through once very quickly, and then we'll go for problems. So let be the step size used in the, let h be the step size used in the integration. The truncation error for simple trapezoidal rule with 2 points is given by, h cube by 12 into f double dash epsilon. So this is the remainder term. We have approximated for a trapezoidal rule, n equal to 1 means the first two terms will come up to, then the second derivative term involved will have the error. So we are neglecting from that. So this will be the error. Now for simple trapezoidal rule, for trapezoidal rule with n1 intervals, composite trapezoidal rule, we will not go into it. In any case, the absolute error for the simple trapezoidal rule is given by this maximum of modulus of this expression throughout. So truncation error of the trapezoidal rule is this. Okay. So truncation for simple trapezoidal rule with 3 points for Simpson rules. This is for trapezoidal rule. This is for Simpson's rule. Okay. All right. Now I'll just go into problems that have come in the previous GATE papers. So now let us go through this. Now, trapezoidal rule. So trapezoidal rule for integration gives exact result when integrand is a polynomial of degree but not 1. That means anything but not 1. 1 but not 0. 0 or 1 or 2. So trapezoidal rule, if you see the interpolation, the degree of the polynomial, see, is a straight line. Straight line usually means a polynomial of degree 1. However, there can be points when in trapezoidal rule we are joining 2 points which have equal function value. So you will get a constant. So polynomial integrand, the degree can be 0. So that's why it is 0 or 1. Mostly it is 1, but sometimes it can be 0. Okay. This is rule, trapezoidal rule. Now, okay. Now this is an value of x at this. The differential equation dx by dt is e power minus 2t into ut has to be solved using trapezoidal rule with the step size h as 0.01. The function ut indicates the unit step function. The function now, if f x x naught is equal to 0, that means at t equal to 0, x is 0, then the value of t at value of x at t equal to 0.01 second. That means how do you approximate this? This is the question. So he's not asking for actual trapezoidal integration. He is saying what will be if we are integrating using trapezoidal, what could be the value of this function. So it is basically solving of the differential equation. Okay. So just a second. Yeah. So first things here, the integrand, this u of t is the unit step function, which means it is 0 for t less than 0 and it is 1 for t greater than 0. This is the unit step function. So now dx by dt is e power minus 2t into u of t. So x will be integral dt. Now, of course, we want that at the first step interval, what will that be? That means, so x equal to, suppose we integrate from t equal to 0 to t equal to 0.01. So what will be the integration? So now, when t is less than 0, when t is less than 0, ut will be 0. When t is greater than 0, it will be equal to 1. So we are left with integral 0 to 0.01. We get e power minus 2t dt. So integrating, we will get no by okay, when we use the trapezoidal rule, suppose we are integrating using trapezoidal rule, the integration will be h by 2 into y naught plus y1, right? So h is 0.01 upon 2, y naught is e power minus 2 power 0 into u of 0 plus y1 e power minus 2 power 1, 2 into 1 to u of 1. So you get 0.01 by 2. This is 1 plus, sorry, this is e power 2 t. Okay. This is 2 into, sorry, 0.01, 0.01, not 1. So e power minus 0.02. So this will be the step. So 0.01 upon 2 plus 1 times, let us calculate, e raised to the power so it is 0.98. So 0.9802. So we'll approximate this. Okay, plus 1 divided by 2 multiplied by 0.01. So we get 0.0099. This will be the next step of integration. So this is the answer. So what did we do? We have to do the solving of differential equation, but we want the next step. What will be the function value at the next step of integration? So this integral, we are using trapezoidal rule here. So use of trapezoidal rule comes here. And we have used h by 2 into y naught plus y1. That's what we did. So y naught is 0 and y1 is 0 point at 0.01. So this is how we find that. Next question. Now, area under the curve shown between area under the curve shown between x equal to 1 and x equal to 5 is to be calculated. using trapezoidal rule. The following points of the curve are given. The evaluated area in meter square. What will that be? We have to do this problem. This question, there's a typo. This has to be x equal to 3 because only 3 coordinates are given. So we need to do this evaluation using trapezoidal rule. So answer is very, very simple. How do we do for trapezoidal rule? So integral y from x equal to 1 to x equal to 3 dx. Okay, using trapezoidal rule. So between these 2 points, we have to use the trapezium. H is 1. In both these cases, h is 1. So h by 2 into 1 plus 4 plus h by 2 into 4 plus 9. That's what, no? Each one is a trapezium, right? What we do is h by 2 into y0 plus y1. The next term is h by 2 into y1 plus y2. So on. So we have only 2 here. So we get this. So we get 1 by 2 into 1 plus 2 into 4 plus 9. So this is 10 plus 8, 18. So the answer we get is 9. So this is a simple, very, very simple calculation of trapezoidal rule. Okay, we are just adding trapeziums. We just have to remember this result. Okay, we'll do the next problem. On trapezoidal rule. Okay. These are the intervals given. Function f is known at the following points. The question is, the value computed using trapezoidal rule. So what is the value of integral 0 to 3 computed by trapezoidal rule? So very simple. Now, what is the value of h? You can see here 0.3, 6.9. So h is 0.3. H is 0.3. Now integral 0 to 3 f of x dx is h upon 2 y naught plus 2 times y1 plus y2 plus y3 up to yn minus 1 plus yn. Summation of all the trapeziums basically. So this is h by 2. H is 0.3 upon 2. Y naught is 0. 2 times of, add all this, 0.09 plus 0.36 plus 0.81 plus plus 9 here. So let us do this calculation now. This one. So 0.09 plus 0.36 plus 0.81 plus 1.44 plus 2.25 plus 3.24 plus 4.41 plus 5.76 plus 7.29 is equal to this multiplied by 2 plus 9 divided by 2 into 0.3. So 9.045 is the answer. Let us see if the options are there. Yes, option is there. 9.045 is the answer. So we have just applied the trapezoidal rule. Okay. So this was problems on trapezoidal rule. We'll do some problems on Simpson's rule. Okay. So Simpson's rule gives exact result when f of x is a polynomial of degree 2. If it's a polynomial of degree 2 and we are making an approximation of 2, so a parabolic approximation, so it will exactly match. So this is Simpson's rule. Next, uh, the order of error in Simpson's rule for numerical integration for step size h. See the order, we discussed this earlier. H bar 4. Okay. So here you get h bar 5 by 90 into fourth derivative. The fourth derivative, when we write, we will write this fourth derivative like this, delta cube, whatever that error, y3 minus delta cube y2 upon h. So h cancels and we get this is proportional to h bar 4. So in this result, the order of error will be h bar 4 for numerical integration. Now let us calculate problems on Simpson's rule. So value of this integral using so we need to solve this. The value of integral 1 by x integrated from 1 to 2 using 1/3 Simpson rule with a step size of h. So let us write x and let us write y. Now starts with 1. Then the next value is 1.25 because 0.025. Then 1.5, 1.5, 1.75 and 2. So we have to integrate from 1 to 2. So you have 5 points. So 1 and 2 such intervals. Now y value will be, y is 1 by x here. F of x is 1 by x. So 1 by 1 is 1. Then 1 by 1.25. So 1 divided by 1.25 is 0.8. 0.8. Then 1 divided by 1.5. So 0.6666. So 0.67. We'll truncate at 2 decimals. Oh, he has not given. He has given 5 decimals. So we'll have to depends on the answer. So we'll use 5 decimals. 0.66667. Then at 1.75, the value is 1 divided by 1.75. This is 0.571428. So 143. 0.57143. Next, at 2, 1 by 2 is 0.5. Now, according to Simpson's 1/3 rule, it is, h by 3 into y naught plus 4 times of y1 plus. So here we have x1, x2, x3, x4, x5. So basically, because only 2 units are there, 1, 2. So we have to choose 3-point interval. No? So 1 to 1.5, 1.5 to 2. So we get 4y1 plus y2 here. Okay, this is y naught, this is y1, this is y2, this is y3, this is y4. Plus h by 3 times y2 plus 4y3 plus y4. So we get h by 3 times y naught plus 4 times y1 plus y3 plus 2 times y2 plus y4. So this is our solution. So h step size 0.25 by 3 times y naught is 1 plus 4 times y1 0.8 plus y3 0.57143 plus 2 times y2 66667 plus y4, that is 0.5. So let us do this calculations. Zero 0.8 plus 0.57143 multiplied by 4. So this is 1 plus 5.4972 plus 2 into 0.66667. So 1.3334 plus 0.5. So now let us do this. Plus 5.4972 plus 1 plus 0.5, 1.5. Divide this by 3. And multiply it with 0.025, 0.25. So we get 0.69421. Okay, I don't know where the 0.69421. Hope we will make
Sir, last step, one place 5.48572.
1 plus 5 point.
48572.
This one.
Yes.
Let me check. 0.8 plus 0.57143 multiplied by 4. 5 point. Okay, I made this mistake. 48572. So now I should be getting correct value, I think. 5.4857572 plus 1.33334 plus 0.5 plus 1 divided by 3 into 0.25. So we are getting 0.693255. 69325. So looking at the answer, C is the correct option. So here, see, the question is simple, but see the error. We have 5 decimals. If you change the decimals, you will get very difficult to solve. So that's why, depending on the decimal, you should increase the approximation length. At what level we want the accuracy. Okay, one more problem we'll do. So all are Simpson's 1/3 rule. They match the correct options. Simpson's 3/8 rule is order of fitting polynomial is third order. Trapezoidal rule first order. Simpson's 1/3 rule second order. So PQR will match with P to 3, Q to 1, and R to 2. So 3, 1, 2. So D is the correct option for this one. This is 1, 2, 3. These are simple ones. 1 by x, 1 by x, so many 1 by x problems. This is function is not known. Again, we'll do for practice. We will do the fourth one and one of these, sixth one maybe. So if the intervals of integration is divided into two equal intervals of width 1, the value of definite integral using Simpson's 1/3 rule is this. So, so x, this is x naught, x1, x2. This is 1, 2, 3. The interval 1 to 3 has been divided into with width 1 set. So 1, 2, 3. So y naught will be log 1, log 2 to the base e, and log 3 to the base e. So this is y naught, this is y1, this is y2. Okay. Now, according to Simpson's 1/3 rule, the approximation is h by 3 into y naught plus 4y1 plus y2. So h is 1 by 3, y naught log 1 is 0 plus 4 times log 2 to the base e plus y2 is log 3 to the base e. So now let's calculate this one. So log x. So 2 log. Log 2 is this plus 3 log. Oh, I made a mistake. So log 2 is this multiplied by 4 gives this plus log 3 is this divided by 3. Somewhere we made an error. No, it is correct answer is 1.29. Correct. This is 1.29. The option printed here is wrong. This is 1.29. This is the correct answer. Last one, last problem for the day. So Simpson's 1/3 rule. Now the interval size here in this particular case, this is the table of functions given. Interval size is 0.25 and this is the function value, the value of integral of function bit from limit 0 to 1 using Simpson's rule. So integral, we get h upon 3 y naught plus 4y1 plus y2 plus h upon 3 y2 plus 4y3 plus y4. So h upon 3 times y naught plus 4 times y1 plus y3 plus 2 times y2 plus y4. This is what we get. H upon 3 is 0.25 upon 3. Y naught here is 1, 4 times y1 plus y3, that is 0.9412 plus 0.64 plus 2 times y2, that is 0.8 plus 0.5. Okay. So let's see this. 0.9412 plus 0.64, 1.5812 multiplied by 4. So 6.3248. 1 plus 6.3248 plus this is 1.6 plus 0.5. So what we get? Plus 1.6 plus 1.5 divided by 3 multiplied by 0.25, 0.7854. So by Simpson's rule, we get this estimate. All right. So you can take previous year's question papers and classify. I'll try to share this. These are further questions on Simpson's rule. I'll give with the answers. On Tuesday, I will take a class. Tomorrow, I'll not be able to take a class. Tuesday, I will take a class on solving differential equations numerically. So we have Euler's method and Runge-Kutta method. These are the two, and we'll solve some problems. Okay, thank you.